You ever shuffle a deck of cards and wonder, just for a second, is there some kind of deep math going on here? Well, spoiler alert, there is. And it's elegant, it's powerful, and it's way deeper than you might think. Today, we're going to decode the mathematics of shuffling by exploring this incredible idea called the symmetric group.
So here's what we're going to do. We'll start with a really simple puzzle, then we'll build up a whole new language to talk about shuffling. After that, we'll uncover the hidden rules of the game. And finally, we'll see how this super abstract idea is actually critical for things like secret codes and sending data across space. It's going to be fun.
All right, first up, the permutation puzzle. We're going to kick things off with a question anyone can answer, just to get a feel for what we're really talking about when we say shuffling. Okay, so picture this. You've got 3 different things on your desk. Maybe your phone, your keys, and a coffee mug. How many unique ways can you line them up? Just take a second and think about it.
The answer is 6. And for those of you who've done some math, you might recognize that as 3 factorial. Now, this collection of all 6 possible arrangements, it's not just a number. It's a complete mathematical object, and it has a name, the symmetric group on 3 elements, or S3 for short.
So each one of those 6 arrangements is what mathematicians call a permutation. Now, the fancy definition is a bijection of a set to itself, but don't let that scare you. All it really means is a specific shuffle, where every item ends up in exactly one new spot. It's just a rearrangement. Okay, to really start digging into these shuffles, we need a way to write them down that's better than just drawing pictures. And, as you'd guess, mathematicians came up with a special notation that is just incredibly powerful. So, one way you could do it is with what's called 2-line notation. The top row is where everything starts, and the bottom row is where it all ends up. So here, 1 moves to where 2 was, 2 moves to where 4 was, and so on. It works, sure, but it's a bit clunky, right? You can't really see the action.
But now, check this out. We can describe that exact same shuffle using something called cycle notation. And this is a total game changer. You read it like a story. 1 goes to 2, which then goes to 4, which goes to 5, and then 5 cycles all the way back to 1. Oh, and 3? It just stays put. This notation doesn't just list the results, it shows you the dance.
And this comparison just lays it all out. Cycle notation isn't just a shorthand, it tells you the story of the shuffle. You can immediately see the structure, a group of 4 elements chasing each other in a circle, and 1 element that's left alone. That whole pattern was totally invisible before.
Now, this collection of shuffles, this S_n thing, it's not just a random bag of operations. It's a group. And in math, that's a big deal. It means it has structure. It means it follows very specific rules. And one of the first most important rules is how you combine 2 shuffles together. If you do one shuffle and then another one, you read the action from right to left, always. You apply the shuffle on the right first, and then you apply the one on the left to that result.
This leads to a really fascinating and kind of weird property. Unlike with numbers, where 2 times 3 is the same as 3 times 2, with permutations, the order you do them in matters a lot. Swapping 1 and 2, then swapping 1 and 3 gives you a totally different result than doing it the other way around. This property is called Non-Abelian, and honestly, it's a huge part of what makes these groups so rich and interesting.
So now that we have this powerful language of cycles, we can start to classify permutations. We can start sorting them into different families based on their fundamental structure, their shape.
And the way we do that is with something called cycle type. It sounds a little formal, but it's super simple. It's just the lengths of the cycles that make up the permutation. That's it. You can think of it as a unique fingerprint, or even the DNA of that specific shuffle. Let's go back to our old friend S3. Remember, it has 6 elements. Well, using this idea, we can see they all fall into 3 distinct cycle types. You've got 2 big 3 cycles, you've got 3 simple swaps, and you've got the 1 do-nothing permutation, which is just 3 1 cycles. And if you look at it visually, it's pretty stark. Half of all the possible shuffles on 3 items are just simple swaps. The other half is split between those 2 big cycles and the identity. Every single one of the 6 permutations fits perfectly into one of these categories. Okay, this brings us to a much deeper question. The permutation 1-2 and the permutation 2-3, they look different, right? But they feel the same. They're both just a simple swap between 2 items. So how do we capture that idea mathematically? When are 2 shuffles fundamentally the same shape?
The answer is a beautiful concept called conjugacy,
And the best way to think about it is simply relabeling. If you take a permutation, like our 3-cycle 1, 2, 3, and you conjugate it by some other shuffle, all you're doing is seeing that same 3-cycle structure, but with the numbers relabeled. The structure itself, the 3-cycle-ness of it, doesn't change at all.
And this leads us to the big reveal, the punchline that ties this whole thing together. Two shuffles are conjugate, meaning they have the same fundamental structure, if and only if they have the exact same cycle type. That fingerprint we were talking about? It turns out it's everything.
And you can see this theorem working its magic right here for S4, the group of shuffling 4 items. It has 24 elements in total. There are 5 possible ways to partition the number 4, which gives us 5 possible cycle types. And what do you know? There are exactly 5 corresponding conjugacy classes. It's a perfect one-to-one match. It just works beautifully.
So, you might be thinking, okay, that's a neat pattern, but why does this matter? It might seem like a really abstract puzzle, but this deep understanding of permutation structure is actually fundamental to our modern digital world.
And here's the connection. In coding theory, the math that powers all of our digital communication, we're obsessed with symmetry. The automorphism group of a code is the set of all the shuffles you can apply to a digital code without changing its core properties. It is, literally, the group of symmetries of that code.
And understanding these symmetries is absolutely essential. It's how we build powerful error-correcting codes that let satellites beam data through a noisy atmosphere. It's used in cryptography to build secure systems. The abstract structure we've been exploring is the bedrock of modern, reliable, and secure communication.
So, the next time you shuffle a deck of cards or even just rearrange things on your desk, remember what's happening under the hood. You're performing an operation in a symmetric group. It really makes you wonder, doesn't it? What other simple, everyday actions are hiding a whole world of complex and beautiful mathematics just waiting to be decoded?